So I'm going to talk about the history of discovery of the first Yang-Mills gauge particle, the gluon. So the Yang-Mills non-abelian gauge particle, the gluon, was discovered at the E plus E minus collider Petra at Daisy in the late spring of 1979. It is the second gauge boson to have been discovered experimentally, the first one being the photon, more than 50 years earlier. The gluon is the Yang-Mills non-abelian gauge particle for strong interactions. The strong interaction between the quarks are mediated by the gluon. As you all know, the exchanged particles responsible for the interaction are called gauge particles. Up to 1979, the only gauge particle that has been observed experimentally, as I said, is the photon. Young and Mills predicted that there is a fundamental difference between the gluon and the photon. The photon cannot emit or absorb another photon, while the gluon can emit and absorb another gluon. This means the gluon has self-interactions, while the photon does not. The experimental discovery of the gluon is the first discovery of the Yang-Mills non-abelian gauge particle. The gluon discovery was followed 4 years later in 1983 by the second and the third Yang-Mills gauge bosons, the C and W at CERN. This talk gives the history of the discovery of the gluon via the observation of three jet events from the process: electron-positron collision go to quark, anti-quark, and the gluon. The gluon was discovered, as I said, at Petra in late spring 1979. So the Petra was a collider, a 2.3 kilometer electron-positron storage ring located at the German National Laboratory Daisy in Hamburg. This laboratory was established in 1959 under the direction of Willy Janschke and has played a crucial role in the re-emergence of Germany as one of the leading countries in physics. The proposal for this project was submitted to German government in November 1974, and it was approved 1 year later. It's something we can feel envious. The heroes of the construction of Petra was Gus Voss. Under his leadership, the electron beam was first stored on July 15, 1970, 9 months ahead of schedule. I don't think you ever hear about that. Petra started its operation in November 1978 at 13 GeV center mass and increased to 27 GeV in the spring of 1979. Eventually, maximum energy was 46 GeV in 1984. So at the Petra storage ring at Daisy, there are 4 experiments: JADE, Pluto, Mark J, and Tasso. Those are the 4 experiments to see the 3 jet events. So the Tasso detector was constructed and operated by collaborating efforts of 90 physicists from 9 institutions in Germany, England, Israel, and United States. So the institutes are RWTH Aachen, University of Bonn, Daisy, University of Hamburg, these 4 institutions from Germany. Then Imperial College, Oxford University, Rutherford Lab from England. And finally, Weizmann Institute from Israel, University of Wisconsin from USA. The TASO detector consists of the following elements. We have a set of proportional chamber and drift chamber inside a 5 kilogauss solenoid magnet to measure the momentum of charged particles. There's a system of liquid argon shower counter to measure the energy of the photon and electron. And then a system measure the muon, and time of flight system, luminosity monitor. And there are also 2 spectrometer arms to identify photon, electron, muon, pion, kaon, proton, antiproton, etc. But at the beginning of Petra turn-on, the most important part of the detector is the excellent performance of the central tracking chamber, which is crucial for the discovery of the first Yang-mu gauge particle. So I won't go through the component of the experiments. So this is a picture of myself and Byung-Week. We were relaxing after tedious work on the drift chamber cabling. The cable carried the time information from the preamplified boxes to the with our electronics. The discovery of the gluon required direct observation. Since the gluon is the gauge particle for strong interactions, the simplest way to produce a gluon is by gluon-Baumstrom process. Electron, positron go to quark, anti-quark, and a gluon. In 1975, this machine Spear at SLAC was the first to observe a 2-jet structure in E plus E minus go to quark, anti-quark. Since the gluon, very similar to the quark, is expected to hadronize into a jet, therefore this particular process will be a 3-jet event. So the question we're going to ask, is the initial energy of Petra when the turn-on in 1978, 1979, high enough to see 3-jet events in the process E plus E minus go to quark, anti-quark gluon? At that time, most of the physicists believed it would not have enough energy initially. In 1978, I made the following rough estimates. So a Spear at SLAC, the center of mass energy is 7.4, and they saw pair of back-to-back jets. Therefore, the invariant mass of the pair of jets is 7.4 GeV. So at Petra, if you see a 3-jet event, the most favorable kinematic situation is the 3 equal energy jets separated by 120 degrees, like a Mercedes-Benz signal. So therefore, the invariant mass of any 2 pair of the jets should be the same as the Spear center mass energy. So the invariant mass of any pair in the 3-jet event at Petra is square root of 3 times E2. E2 is the energy of the jets. It should equal to 7.4 GeV, the Spear center mass energy. So we solve this extremely simple equation. The energy of the jet at Petra should be 4.3 GeV. So since you need 3 jets, so therefore the total energy would be 13 GeV. So this 13 GeV need to be increased because each jet is narrower in Petra than in Spear because you're producing 3 jets. So we estimate that the additional energy should be 50% higher, leading to about the center of mass energy at Petra 20 GeV. And further phase-based consideration increase this energy by 10%. So our estimate is that if Petra reach 22 GeV or above, we should begin to see 3-jet events. Then once we have enough energy, the question is, how do we find 3-jet events? At those days, the graphics are not very advanced, so we have to be smart. By energy momentum conservation, 2 jets in E plus E minus go to quark, anti-quark has to be back to back. Therefore, 3 jets in E plus E minus go to quark, anti-quark, and gluon had to lie on the plane. So the search for a 3-jet event can be carried out in a 2-dimensional event plane, the plane that formed the momentum of quark, anti-quark, and gluon. It is very simple. So in May 17, 1979, I myself and my postdoc, we published a paper called A Method of 3-Jet Analysis in E plus E minus annihilation. So then later on, we used this method to find the first 3-jet events at the center of mass energy at Petra in June 79, when the Petra energy just enough to produce 3-jet events. So the algorithm is the following. We first determine the event plane in which the quark, anti-quark, and the gluon lies. So to find a plane where the sum of the square of the transverse momentum of all the particles is minimized. Then we project all the measured momentum onto this event plane and rearrange them in a cyclic order. We group this particle into 3 sets and choose the group by minimizing the sum of the 3 sphericity of each set of a contiguous momentum vector. So these 3 sets I identify as 3 jets. Once we have 3 jets, the 3 jet I identify, we can then study the characteristic of a jet by studying the average transverse momentum of the jets. So this is the first 12 pages of my notes on the jet analysis. So the computer program for this algorithm was ready in the fall of 1978. In early 1979, Petra started to run at 13 GeV and 17 GeV, but we found no 3-jet events. But by June 1979, a few days before the Neutrino 79 International Conference in Bergen, Zubanek and I found one gold-plated 3-jet event out of 40 hadronic events collected at this new center of mass energy, 27.4 GeV. So Bjorn Wiik was scheduled to give a plenary talk in the Bergen conference, and his talk title was First Result from Petra, and he showed these events. So this is events that Bjorn Wiik has shown in the Bergen conference, and these events look like the Mercedes-Benz symbol. So in his talk, he said, if a hard gluon bombstorm is causing the large PT value in the plane, then a small fraction of the event should display a 3-jet structure. The event were analyzed for a 3-jet structure using the method proposed by Wu and Zubanek. A candidate for 3-jet events observed by Tasso group at 27.4 GeV is shown in figure 21, view along n3 direction. That means you minimize the transverse momentum on the plane. Note that the event has a three clear, well-separated jets, and it's just not the widening of a jet. So as soon as we returned from Bergen, we wrote the tassel notes on the first three jet events. So before the question of statistical fluctuation of one event could seriously be raised, we saw more events in E plus E minus dodecahedron at the center mass energy 27.4 GeV, and the events were rolling in, and we found more three-jet events. Less than 2 weeks after Bergen conference, 4 tassel three-jet events were shown by Paul Zoding at the European Physical Society conference in Geneva, 27 June to July 4th. So these are the 4 three-jet events shown by Paul Zoding in the EPS conference. And he also showed a number of distributions which give the characteristics of the three-jet events. With the three-jet events, you can ask, what are the three jets? Since quarks and antiquark are fermions, and the electron positron are 2 fermions, you cannot turn 2 fermions into 3 fermions. So these three jets cannot be all quark or antiquarks. So the experimental observation of three-jet events in E plus E minus annihilation implies the discovery of a new particle. Similar to quarks, this new particle hadronizes into a jet. Therefore, it cannot be a color singlet. So it cannot be a pion, kaon, proton, and so on. So these three-jet events are therefore most naturally explained by a hard non-collinear Baumstrom from the quark or antiquark. E plus E minus go to quark, antiquark, and a gluon.
Can you possibly go back to the 4 jets that were shown and identify things a little longer there, because I couldn't work out quickly enough which was the gluon?
I don't think we can do that. I think later when we have a lot of events, we do identify the gluon jet being the softer one, larger average transverse momentum of the particle inside the jets. But at the early days, they're just statistical. But with just see three jet, you cannot tell which one is gluon jet. You can guess. The one with a lower energy may be the gluon jets. So I quoted what European Physical Society said. These 2 talks at the Bergen or EPS Geneva conferences generated considerable interest and stimulated an enormous analytic efforts, because the only viable interpretation was based on the creation of gluons by quark Baumstrom. So 2 months later, at the Lepton-Photon Conference at Fermilab in late August 1979, all 4 experiments at Petra, J, Mark J, Bruto, and Tasso, gave more extensive data confirming the earlier observation of Tasso. As soon as there were enough data, the Tasso collaboration determined the spin of the gluon to be indeed 1 in September 1980. 1 month later, the Bruto collaboration reached the same conclusions. This result was confirmed subsequently by the other Petra experiments. The method we use for determination of the spin, we use the proposal from Alice Kalina. So this is a picture taken at the European Physical Society meeting 1995, where the high energy and particle physics prize were given to 4 of us. I want to show you Gunther Wolff, the first one on the left, Bjorn Wieck, Paul Zoding, and myself. Unfortunately, Bjorn Wieck, a few years later, he died by falling off a tree. So I listed a number of papers in the early days concerning the free-jet event. I will not go through them. So now I want to go through with you the recent developments, the important role gluon in the Higgs discovery. The gluon, as I say, the Yang-mu non-abelian gauge particle for strong interaction, was discovered 36 years ago. During this 36 years, it became more and more important. One prominent example is its role in the recent discovery of the Higgs particle by the ATLAS and CMS collaborations at LHC. This observation, as you all know, of the Higgs particle in 2012 had led to award of 2013 Nobel Prize in Physics to Englert and Higgs. Braut unfortunately died a year and a half earlier. Since the gluon is the Yang-mu gauge particle for strong interaction, to a good approximation, a proton consists of a number of gluons, in addition to 2 up quark and 1 down quark. Since the coupling of the Higgs to any elementary particle is proportional to its mass, therefore there's very little coupling between the Higgs particle and those and other constituents in the proton. Therefore, for some heavy particle need to be produced in a proton-proton collision at LHC. And then we use this coupling to the Higgs particle. Among the known elementary particles, the top quark with the mass 173 GeV is the heaviest. So this is the way Higgs is produced by the gluon going through a loop of top quark, and then the 2 quark a virtual top quark will annihilate into a Higgs. So because the color conservation, the gluon has color, but not the Higgs particle. The top anti-top pair produced by gluon cannot annihilate into a Higgs particle. In order for this annihilation into a Higgs particle to occur, it is necessary for the top or the anti-top quark to interact with a second gluon to change its color content. So therefore, it is necessary to involve 2 gluons. So 1 from each proton of the 2 beam from LHC. So you can see that there are 2 gluons involved, and this process is called gluon-gluon fusion. So as expected from the large mass of the top quark, the gluon-gluon fusion is by far the most important Higgs production process. So about 90% of the Higgs production cross-section come from gluon-gluon fusion. In this way, the gluon play a very central role in the discovery of the Higgs particle in 2012. I make a dramatic sentence by saying that if there were no gluon, the Higgs particle would not have been discovered so soon. So this is a cartoon I made that the two proton, the gluon inside the proton will produce the Higgs particle decay into two photons. Okay, my conclusion. The experimental observation of three-jet event in E plus E minus annihilation, first accomplished by tarsal collaboration in the late spring of 1979 and confirmed by all four experiments at Petra 2 months later in the summer. Since two fermions, E plus E minus, cannot turn into three fermions, three-jet event imply a discovery of a new particle. Similar to quark, the new particle hadronizes into a jet, therefore cannot be a color singlet. These three-jet events are most naturally explained by the hot non-collinear Barmstrom E plus E minus go to quark anti-quark gluon. 1 year later, the spin of the gluon was determined experimentally to be 1, as you expected from young mu gauge particle. The 1979 discovery of the second gauge particle, the gluon, occurred more than half a century after the first one, the photon. The second gauge particle is, of course, the first young mu non-abelian gauge particle, a gauge particle with self-interaction. 4 years later, in 1983, the second and the third non-abelian gauge particle, W and C, were discovered at CERN. So since the first observation 36 years ago, the importance of the gluon in particle physics has grown significantly, and especially its role in the discovery of the Higgs particles. The Higgs particles were produced by gluon-gluon fusion in 2012 by the Large Hadron Collider at CERN. If there were no gluon, the Higgs particle could have been discovered a bit later. Thank you.
Thank you. Any questions?
I would just like to make a comment. It's to praise the organizers for having brought in Professor Wu to talk about the experimental difficulties and give us some perspective on the actual field. So I thought your display of the sequence of the experiments and the way the logic had to go was a great contribution.
Very good.
Thank you.
Any more remarks? Okay, we thank the speaker again.
Thank you.